I'm going to start with the very basic pipeline thickness related initial concept, and I hope you will enjoy. And then step by step we will unfold the further details. Okay, let us start. So let me just draw some very simple pictures, and then you will understand what am I talking about. So pipe is of course circular. So let's draw pipe which is a circle, and in this pipe it's of course having a thickness. So I'm going to draw a pipe. I'm also going to draw a cross section of the side view of this pipe, which is going to be something like this. This is the center line. So when we say the pressure P is acting in this pipe, it is going to act in a radial direction. That means it is going to act in a projected area of pipe. Okay, if the pipe we call it as diameter D, which is outside diameter. For the simplicity of the deriving the formula, we will consider only OD. We will not talk about the mean diameter and all that. So OD, and there is a thickness, which is T. So what is going to happen is, and let us say that the length is unit length, which is L or 1 meter, as you wish, you can consider. It's basically unit length. So I am taking a piece of pipe in which, say 1 meter pipe or L length of pipe, in which the pressure is acting like this, and it's a projected area. Okay. Now because of this pressure which is acting, the pipe is going to get separated into two parts. When it's going to fail, it's going to fail suppose across this thickness, at these 2 points, because the pressure is acting, it is getting divided into 2 parts along the length, because the pressure is acting radially. So when it fails, the top view, okay, is this. It's going to look like this. So the pressure has acted, it has got separated into 2 parts, and it has formed this kind of a cross section. Okay, this is like failure cross section, and this is a pipe thickness, metal. Normally pipes are made of metal, okay, carbon steel mostly. Now what will happen is, as you know that the stresses, okay, stress is nothing but force upon area. So let's write down first stress. Okay, here we are talking about hoop stress or radial stress. Okay, is nothing but force upon area. This is a basic principle which I believe everyone knows. So now what we have to do is to calculate, to decide how the pipe thickness is calculated, or for the given thickness and material property, how the what kind of a hoop stress, magnitude of hoop stress that is going to generate in the pipe is what can be calculated, and based on that the allowable stress if you use, then you can calculate the thickness as well. Okay, so basically let's see the hoop stress. Yeah, so force, so how much force is going to act now in this, so which is basically force is acting because of the internal pressure P. Now so force, if you want to calculate, it will become internal pressure P multiplied by diameter D, because this is the diameter and it's projected against this diameter, so its curvature is not considered here. It's basically D. Okay, so P into D is the force acting, internal pressure into D, for the unit length L. Okay, this is acting along the unit length L. So this is the force. Okay, now this force is resisted by the pipe cross section or pipe strength of the pipe metal. Yeah, so but when it's going to fail, or failure theory point of view, the resistance is provided by or offered by this 2 times thickness, okay, of unit length L or 1 meter. Okay, so the resisting area, to calculate the stress that is induced in the pipe, we have to find out the resisting area, which is going to be 2 times T. As you can see here, this is 1 T, this is another T. Okay, T is the thickness, into length L, which is the unit length. So pressure is also acting on the unit length, and resistance is offered also by unit length. Okay. So now if you divide force upon area to calculate the stress, it will become, so basically L will get cancelled out and it will become PD by 2T. Okay. This is nothing but hoop stress. Such a simple formula, but many people know the formula PD by 2T, but how it is derived is not very commonly known. That's why this is the derivation of it. And now you can see that we have now derived this. Now normally in any design what we do is we have to provide the material strength in such a way that it will be more than the induced stress. Okay. Then that means that pipe is going to, if the pipe's material strength and thickness is adequate to overcome the hoop stress with factor of safety, because anything what we design we always consider factor of safety, because we don't want the exact design, we want always some margin for the uncertainties. Okay. So now in hoop stress is basically S. So if you want to calculate now T, thickness of the pipe, okay, to withstand the stress resulting, hoop stress basically resulting from the internal pressure, then we can always do like this, PD by 2S. Now S here is basically hoop stress, but now we want some margin, factor of safety or design margin. So we are going to call this as material strength property, which in pipeline we call it SY, which is nothing but the yield strength of the pipe. Okay, but this is full yield strength, so we want factor of safety. So what we are going to do is we are going to multiply this with factor of safety F, which we are going to call it as design factor. And there are some other temperature factors also which we will see later, but basically don't get confused now with the temperature factor. Basically consider F as a factor of safety. So whatever factor of safety you want, let it be 20%, 25%, 30%, 28%, 40%, that will be applied to yield strength. Yield strength is the ultimate, the material at which, the stress at which the pipe is going to yield. So basically, if you see the pipeline design codes, you will always see the formula for calculating the thickness of pipe is PD by 2 SFET. Now in this, S is SMYS, which is yield strength, F is design factor, E is joint efficiency, because if the pipe is welded and if it has got some kind of a limitation related to welding, some welds might have providing less kind of a strength as compared to the main pipe body, then that efficiency which is always going to be less than 1 or equal to 1, less than or equal to 1. If the welding is perfect, then it can be 1. And T is the temperature correction, basically temperature factor, which is, as we all know that whenever the temperature of any material goes up, its strength reduces. So why in the forging industry, what we see, or basically when we see the metal rod, if you have to bend or create some particular shape of the metal rod, then basically what we do is we heat that, okay, and then we bend it easily. So it's nothing but the material strength reduces on heating. The same thing applies here. So if your pipe is going to experience very high temperature, then its strength will be to some extent reduced. So accordingly you have to add additional thickness margin for that, so that is the reason this is coming. So basically it's nothing but hoop stress. Now you are calculating, instead of hoop stress, you are calculating thickness to resist the hoop stress. That's why this formula comes. In pipeline design, when you have the thickness already selected based on these calculations, later on hoop stress has got a contribution into various stress combinations, which is nothing but longitudinal stress and some kind of a combined thermal and pressure stresses when the pipeline is getting buried. So all that will come later in further lectures, but this is to start with. This is the radial stress called hoop stress. I hope you have understood such a basic simple concept and how hoop stress is derived. Okay, I will explain the longitudinal stress and its particular use in the day-to-day application also I will explain. You will be surprised to see that. So that is in the next lecture. Thank you.